Hello everyone. In this tutorial, we will learn how to establish a multi-operating system environment where we will run Linux kernel on Cortex A55 and FreeRTOS on Cortex M33. We will also run a sample program that will demonstrate the inter-processor communication between these two cores. So we will start off with building the FSP flexible software package for Cortex M33 by adding multi-OS feature package into our build system. We can download this package from the link. So on clicking this, you can download it. So after downloading it, we need to extract its contents, which includes sample programs along with the Yocto layer. So as a first step, we need to extract the contents of this layer. So this layer contains two layers according to the evaluation kit that we need. So one is for RZG12 and the other one is for G3. So we will be using this RZG12. So we need to copy this meta RZ features layer into the project directory where we have our Yocto project configured. So I have already added this one here. Now we will add this layer to the build configurations. So first we will source the environment and then add the layer through bitbake command. Here we can see that our layer is added in the build configuration. Now we are required to build our image again through the bitbake command. Once the build gets completed, you can get the WIC image from the deploy directory as shown in here. You are required to load it on an SD card as demonstrated in the previous videos. Moving on to the next part, we need the eSquare Studio installed in our development PC for code development, generation and debugging. You can download it from Renesas website and according to the operating system that you are using on the development PC. And then you can follow the guideline to install it for RZ series from the link given in the description. Now from the multi-OS package that we downloaded earlier, we need to extract this RP sample program for our relevant board. So we will extract this one as we are using RZG12. Here we have extracted the sample project and now we need to run eSquare Studio. First you can create a new workspace. Now we will import the project that we just extracted. Here we can see the project that we extracted. And first of all, we will set the toolchain for this project. So from the toolchain tab, we will select the toolchain, which is from ARM and the latest version 13 that we have installed here. So the toolchain for the project is set. Now to add the necessary libraries and drivers for the peripherals, we will add another package which is RZG FSP pack to the eSquare Studio. We can get this package from GitHub link from this link and we can download it by clicking here. As this package gets installed, we need to extract it in the installation directory of E2Square Studio. So this is the installation directory of eSquare Studio and in this location project gen, we need to extract it and place the FSP package in here. Now we need to verify that if the FSP package is installed in the path for eSquare Studio or not, which we will do by going to this help section, and from here we will go to CMSys package management, and here we can see that the generic package is installed along with the FSP package that we just added. So our FSP package is installed here. Now we can move towards compiling our sample program, which we will do by clicking on this build button. We can see that there's no error here and the build has completed. So if the project is successfully compiled, it will create output files in the debug directory, which is over here. And we can see that we have got some binary outputs in here which are required for this project. So it will generate some binaries for non-secure code and secure code, which verifies that our project has successfully compiled. Now we need to load these files on the VFAT partition of the SD card where we have already loaded the VIC image. So this is the VFAT partition on which we will load these binary files. So these are the 4 files related to secure and non-secure code that we will load onto the VFAT partition. So copy these 4 files and mount it on this partition. So all the 4 files are now copied. To run the program, we will now set up the hardware. To begin with, set the board to debug mode. For this, we will set the pin 1 of switch 1 to off to enable it in JTAG debug mode. Which is this pin. Insert the SD card containing the VIC image onto the SD card slot on the carrier board. Connect the PMOD USB UART module to the board to enable the serial connection of the Cortex M33. Along with it, we have the serial cable over here, and connect the other side to your PC. For debugging, attach a J-Link debugger, which is this one, along with the 9-pin connector cable. So we will connect this connector cable to the debug port, which is CN2 on the SOM module. And connect the other side of the J-Link debugger to your PC. It will then power on. With the hardware setup complete, power on the board. The board should boot up properly. And we need to stop it at its U-boot. So we will reboot it and then hit enter to enter the U-boot. Here we will load all the sample code files to invoke the RP message sample program from U-boot. So let's start running the related commands. First of all, we will disable the D cache so that we can access the memory directly, and then set the SD card as active device. Now we will begin to load files one by one. So all the 4 files are now loaded. Now we will run the CM33 command to start debugging Cortex M33, initializing the secure vector and non-secure vector. And then enable the D cache again. And now we can boot the system. Now let's start debugging the sample program on eSquare Studio. Click here to start the debugging. On starting debugging, a debug perspective will open up if it's the first time for you. And the system will enter a warm reset state. So here it has achieved the warm reset state. To proceed, click again to begin debugging from the main function. And once initiated, the program will start running. So here on Cortex M33, we can see that the sample program has been started and is waiting for the establishment of RP message channel between Cortex M33 and Cortex A55. So now we need to run the sample program on Cortex A55. So now here on the Cortex A55, run the RP message sample program. And we are required to input the channel on which we need to communicate. So I will enter one here. And here you can see the connection is established between the two cores. And now we will go through these messages. Here we can see the communication established and Cortex A55 started to send messages to Cortex M33. And M33 receives the messages sent from Cortex A55 and the echo reply is sent back from Cortex M33. After the last payload, the application terminates with these logs on Cortex A55, and on Cortex M33 it terminates by deinitialization of remote processor. And then again Cortex M33 waits for communication as it is the server endpoint in this setup. So we have successfully demonstrated multi-core communication using RP message protocol in this tutorial using RZG2L evaluation kit. Thanks for watching and see you in the next video.